this. We finished 9.2 last time. So let's do 9.3 today. So in 9.1 we talk about the sequence. In 9.2 we talk about the series. Okay, if you add all the numbers in the sequence, that's called the series. Okay, and then the sum of those infinite number of numbers could be convergent. It means you get a finite number for the sum, or it could be you know, blowing up. That's called the divergent. All right. We don't get a fixed finite number for the sum of those infinite many numbers. That's called divergent. So we have two types of results for the series, and then we're going to discuss the strategies or techniques to determine whether a series is convergent or not. Whether you add up all those infinite number of numbers, you get the finite, the fixed number or not. And we have quite a few strategies or methods, and we're going to start from one by one. So the first method we discuss is called the integral test, and that's the topic today. And we're going to talk about the series later. Okay, so the integral test says if we have function f, a positive function, and it's continuous, and it's also decreasing for x greater than or equal to 1. Okay, so we got the well-behaved function. Okay, it's positive, it's continuous, and it's decreasing. And a sub n equal to f of n. All right. So there's a connection between the sequence and the function. Basically, if you draw the graph of the function f, and then you just pick out the those points on the curve, and to make a sequence, and then you add up all those numbers in the sequence, you get a series of an. Then it says, the theorem says, that theorem 9.10 says, then the series a and the integral of f from 1 to infinity, either both converge or both diverge. So you can determine the convergence property of the series from the integral of the function. Okay, if the integral of the function from 1 to infinity is a finite fixed number, then the sum of the series also is a finite fixed number or convergent. If the integral of the function from 1 to infinity diverges, or you get the infinity, it's not a finite number, then the series a and also is divergent. Okay, you don't get finite number, a fixed finite number for this infinite and many numbers sum. All right. So that changes the problem of summation into a problem of integral, and we know how to handle integrals more than sums. We basically don't have too many ways to tell whether the sum of infinite many numbers give you a finite number or not. We just have a few series. We discussed them. The geometric series, and we got another one called the telescoping series. Other than that, we don't have anything to use, to determine a series conversion or not. But we know how to integrate functions pretty well. So that makes the problem a little easier. Okay, so let's do one example by using this method of the integral test. So let's call the integral test. You can use the integral to determine the convergence property of a series. So in this example, we need to determine convergence or divergence of the series of n over n squared plus 1. Okay, so so if we want to use the integral test, we have to define the function f. They're not given the problem, but that's easy. Now, basically, you just change n's in this terms of the sequence series into x. So, you know, an is just the n over n squared plus 1. Then you just change n to x everywhere in n. We get fx equal to x over x squared plus 1. So that's the function we deal with. Then obviously an equals the f of n, because that's how we define the fx. Okay. Also, we have to check the conditions for this theorem. We need to make sure f is positive, and that's always true, because when x is greater than or equal to 1, x over x squared plus 1 is obvious positive, and it is continuous, all right? There's nothing in this function to make it discontinuous, especially the denominator x squared plus 1 is always greater than or equal to 1. So it can never be 0, and that makes the whole function continuous in the whole domain, all right? Well, the other thing, to make sure the function is decreasing for x greater than or equal to 1. That's the other condition we need to check. So we have learned the calculus, so we can use the derivative to determine a function is increasing or decreasing by checking sign of the derivative. When the derivative of a function is positive, then the function is increasing. When the derivative of a function is negative, then the function itself is decreasing. So that's why we need the tools of calculus in the series in this chapter. So just take the derivative of the function and see what happens. So this is the quotient rule we use. It's a rational function, so we have to use the quotient rule, all right? And so the quotient rule says the derivative of quotient of two functions, f over g, is f prime g minus f g prime over g squared, okay? So f is just x and g is just x squared plus 1. So we get x prime times x squared plus 1 minus x times x squared plus 1 over x squared plus 1 to the square. And the derivative of x is just 1, and the derivative of x squared plus 1 is 2x. So we just, get this result. 1 times x squared plus 1 minus x over 2x on the top, and you can simplify it by, multiplying out to get x squared plus 1 minus 2x squared on the top. And you don't change the denominator. So then you get 1 minus x squared if we combine x squared with 2 minus 2 with negative 2x squared. So then it's indeed less than or equal to 0 if x is greater than or equal to 1. Remember, we got 1 minus x squared on the top. So if x is greater than 1, then you get the derivative negative. It's equal to 0 when x equal to 1. The derivative is 0 only when x equal to 1. So if x is decreasing, indeed, for x greater than or equal to 1. So all the conditions are met for this theorem, so we can use it. And so the next thing you do is to take the integral of this function and see whether it converges or not. So we need to integrate this function f from 1 to infinity, and we know how to do it. It's called improper integral, remember? So you have to integrate it from 1 to b, and then take the limit with b approaching infinity, remember? There are two steps for these types of improper integral. So if you integrate x over x squared plus 1, you need to use the substitution of u equal to x squared plus 1, and then you can easily get the result to be natural log of x squared plus 1. All right? Okay, I think I missed the 1/2 in here. Maybe, I guess. Yes, okay, there should be 1/2 in the front. So it should be 1/2 natural log of x squared plus 1. Sorry about it. So that's the integration. You just plug in 1 to b and subtract. And so we got natural log of b squared plus 1 minus natural log of 1 squared plus 1. So we don't have to worry about the 1 squared plus 1. That's just 1 plus 1 or 2. So, and then 2. And what matters is the first term of natural log of b squared plus 1. When b approaches infinity, this b squared and the b squared plus 1 also approaches infinity. And then, the natural function is increasing without bound. So this natural function has a limit approaching infinity. So that means the improper integral diverges. So by the theorem 9.10, we know the series also diverges. All right, so the sum of all these numbers, infinite many numbers, is not finite. All right, so that's the integrals. Any questions? Okay, let's do another example. This time we need to do a similar problem to determine whether a series convergent or divergent, and the series 1 over n plus 1. So just do the same thing as before. We are going to define a function f based on the terms of the series. Okay, so you just change n to x in the expression of the terms of the series. So then you got fx equal to 1 over x squared, all right, plus 1. And an equals of course, and you have to check all the conditions. Well, obviously this function is positive, everything in this 1 over x squared plus 1 plus, and it is continuous. Obviously, there's nothing make the function to be 0 in the denominator. Okay, and also obviously the function is decreasing because when x increases, x squared increases, and x plus 1 increases, and 1 over x squared plus 1 decreases. Okay, so all the conditions are met, and then you just use the theorem by taking the integral of the function and see whether it converges or not. So when you integrate the function from 1 to infinity, okay, that's always the case. You integrate the function from 1 to infinity, not from 0 to infinity or from negative infinity to positive infinity. Okay, so we integrate this function 1 over x squared plus 1 from 1 to infinity, and that's just arctangent x. Okay, that's you can easily find it from the formula. So we got arctangent x, and you plug in b and 1, subtract, and then you take the limit with b approaching infinity. Okay, so arctangent 1 is powerful. You can easily find out. And then arctangent b as b approaches infinity is power 2. Okay, if you know arctangent function. Right? So it's power 2 minus power 4, so we get power 4. So it is finite. So the integral does converge. So by theorem 9.9, number 10, the series also converges. All right. So you do need to be um, comfortable with the integrals and to be familiar with those integral techniques. All right, integration techniques. Any questions for this example? No question. Then we just go to the next page 3. Now let's talk about the P series and also harmonic series. So and we're going to use the integral test in the P series later. So let's talk about the P series first. What is a P series? What is a P series? The P series is the series of 1 over n to the P. Okay. Remember that means 1 over 1 to the P plus 1 over 2 to the P plus 1 over 3 to the P, where P is any positive number. So the P series here, the P means the exponent of n in the denominator. Okay, and it is a constant for any particular series. So that's a constant. What is changing is n. Okay, remember, for the p series, what changes is n, not p. All right. So if, for example, when p equals 1, so then we get the series 1 over n to the 1. So that's just 1 over n. So we get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. And this particular series is called the harmonic series. Okay, harmonic series is just a special case of p series. Then we can extend the definition term of harmonic series into more general sense. We can define 1 over a n plus b, where a and b are both positive numbers. Okay, and there are constants, and what is changed is n. Okay, in any series right now, we just talk about the n to be changing. Okay, so what is that series? So it's 1 over a plus b when equals 1, and then 1 over 2a plus b is not 21, I'm sorry, when n equal to 2, and it's 1 over 3a plus b when a equal to 3. So you just add all those fractions, and that's called the general harmonic series. Okay, so these are just the definitions. And then we want to know whether the p series converges or not. All right. And it turns out the convergence property of the p series really depends on p only. All right. So here's the theorem that tells when the p series converges and diverges. So theorem 9.11 says the p series of 1 over n to the p converges if p greater than 1 and diverges if p is between 0 and 1, including equal to 1. Okay, we don't consider p to be 0, negative, and that's because that's obviously divergent. Okay, so those are trivial cases. And the proof of this theorem is not very hard, so we can prove it easily by using the integral test. So again, you just change n to x and define a function f to be 1 over x to the p. Okay, again, we consider case p greater than 0 or positive. So obviously an equals f of n, and furthermore, f of x is greater than 0, we got everything positive, all right, because x, we consider the number of x greater than equal to 1, okay, obviously case. All right, so everything is positive. So f is positive and f is continuous. Obviously, you cannot get 0 in the denominator when you have x to the p in the denominator. It can never be 0 because x is greater than equal to 1. All right, so we have two conditions met for the integral test, and then we need to know whether the function is decreasing or not. That's the third condition, remember? So again, we can take the derivative, but I think pretty obvious, if x is greater than 1, then you raise the x to the positive power in the denominator, then obviously as x increases, x to the p will increase, and the 1 of x to the p decreases. But you can also easily check by taking the derivative of this function. You get the the derivative of 1 of x to the p, which can be written as derivative of x to the negative p, and you get negative p times x to the negative p minus 1, all right, using the power rule. And that can be rewritten as negative p over x to the p plus 1. Remember, the negative exponent means that the whole thing in the denominator, all right? So this is indeed the negative because p is positive and the x to p plus 1 is also positive, you know. So and the derivative of f is negative. So fx is decreasing, right? Okay. So we can use the integral, but there's a little complication. In here we have to distinguish between different cases, whether p is greater than 1 or less than 1 or equal to 1. Okay. Because when we do the integral test, when we integrate it, you're going to get a different result for these integrals. So let's just consider the first case when p is greater than 1. Remember, p is always positive, okay? So when p is greater than 1, that means obviously p minus 1 is greater than 0. Okay, keeping that in mind. So let's do the integral test. We need to integrate the function from 1 to infinity, okay, as we did before. So we need to integrate 1 with x to the p from 1 to infinity, and again, that's an improper integral. Do this step by step. Take the integral from 1 to b and take the limit from this b approaching infinity. So you rewrite 1 of x to the p as x to the negative p and using the power rule to get x to the negative p plus 1 over negative p plus 1. And then you plug in 1 to b and subtract and take the limit. Okay. So if you do that, you're going to get the negative p plus 1. That's always the same. We don't change that. And plug in b for x for b for x, you get b to the negative p plus 1. And plug in 1 for x, you get 1 to the negative p plus 1. Okay. And then the first term, b to the negative p plus 1, you can rewritten it as 1 over b to the p minus 1. Okay, you change the sign of the exponents and then put in the denominator. Okay, and the 1 to any power is just 1. All right, so because p is greater than 1, the p is minus 1 is greater than 0 in this case. When you take the limit with b approaching infinity, you get a b to the p minus 1 also approaches infinity because p minus 1 is greater than 0. Okay, so 1 over b to the p minus 1 then approaches 0. So you get a 0 for the limit from the first term, and then you subtract 1 over negative p plus 1. So you get negative 1 over negative p plus 1, or if you multiply a negative sign or negative 1 both on top and at the bottom, you get 1 over p minus 1. Okay, so you indeed get a finite number because p is greater than 1. So you do get a finite number for the integral. So that means the integral converges. So from the integral test, the series also converges. So we considered the first case when p greater than 1, the series converges. All right. And the next case is p greater than 0 and less than 1. Okay. So if you rewrite it as another way, that means negative p plus 1 is greater than 0. Okay. If p is from 0 to 1, and the negative number will be from negative 1 to 0. If you add a 1 to that, you get a positive number. Okay. So again, just do the same steps as we did in the first case. Take the integral of function from 1 to infinity and going through all the steps. We got a similar result. Okay. Everything is almost the same except when you take the limit. So we still get the b to negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1 to take the limit of this with b approaching infinity. Okay. And so what happens is, this time b to the negative p plus 1 approaches infinity because negative p plus 1 is positive. So you raise that power, positive power for b with b approaching infinity. So that the whole thing also approaches infinity. So the result is infinity for this integral. So that means the integral diverges. So the integral test, the series also diverges. So when p is greater than 0 and less than 1, this series, the p series, diverges. And then we still have one more case for p equal to 1 to consider. Okay, let's see what happens when p is equal to 1. So again, you just take the integral of the function from 1 to infinity. This time 1 of x to the p is just 1 of x when p equals 1. Remember the third case. Now you take the integral of 1 of x, you get the natural log of absolute value of x. So you don't get a power function in this case. That's why you need to separate it into the other cases. And then you plug in b and 1 and subtract and take the limit. So we get the n and b minus n and 1 with b approaching infinity. N and 1 is just 0. And the limit of n and b with b approaching infinity is also infinity. The natural log function increases without bound. So by the integral diverges. So by the integral test, the series also diverges. So then you can combine case 2 and 3 to say when p is greater than 0 and less than equal to 1, the p series diverges. All right? So keep in mind, the p series converges if p is greater than 1. All right? Let's do some examples by using the p series. So in the first example, we need to determine convergence or divergence of harmonic series 1 over n. We actually did it in case 3 in the previous page, but let's just review it. Okay, so harmonic series 1 over n is a special case of the p series with p equal to 1. So 1 over n to the p with p equal to 1. From the result of last page, the series diverges. Okay, when p is greater than 1, the p series converges. When p is less than or equal to 1, the series diverges. All right. And so that's one example. And the next example is how about 1 over n squared? Okay, obviously this is p series with p equal to 2. Okay, remember the p series is 1 over n to the p. So we got 1 over n squared, so that means p equals 1 equal to 2. So that's greater than 1. From the previous page, we know when p is greater than 1, the p series converges. So this 1 over n squared, that series converges. All right. Okay, let's just do one more example and then we're done with this section. This time we get a different series, and it's not the p series anymore, but we're going to use the integral test again for this spatial series. We know the series of 1 over n is called the harmonic series, and that's divergent. And the series of 1 over n squared, we got result that's convergent in previous examples. So what happens if the series is 1 over n times an n on n? So that's between n and n squared. So how about this series? Is it convergent or divergent? Okay, so we cannot use the results for the p series because it's not the p series. Okay, it's not just the 1 over n to the p. You get another factor of natural log of n in the denominator. Okay, so we cannot use the conclusions from the p series. We have to do it from the start by using the integral test. Okay, so again, you're going to find a function based on the series. Just change n to x everywhere in the expression of the terms in this series. So we get f of x equal to 1 over x times ln x. So then a sub n equal to f of n, obviously. Of course, if x will be greater than 0 when x is greater than 1. Okay, so remember this uh, this series and then start from 2 to infinity. If you notice that the problem itself, you cannot start from 1 because you get the natural log of 1 equal to 0, then you get the 0 in the denominator of the first term, so it cannot start from 1. It has to start from 2. So then obviously x is also greater than or equal to 2 in the function we defined, and then this function is obviously positive because x is greater than or equal to 2, and ln x when x is greater than 1 is positive. So both of them are positive, so the function itself is positive if you multiply them. And if x is continuous, obviously, there's nothing in the denominator that there will be 0 when x greater than or equal to 2. And an x equal to 0 when x equal to 1. But because x is greater than or equal to 2, so it's always positive. So it is continuous for x greater than or equal to 2. And then, of course, when the function, when x increases, both x and x are increasing. Okay, then x times ln x also increases, and you take the reciprocal, you get 1 over x times ln x, that's decreasing. So fx is decreasing for x greater than or equal to 2, no problem. So all the conditions for the integral test are satisfied. So now we can use the integral test by taking the integral of this function from 2 to infinity. Okay, we don't do it from 1 to infinity because n started from 2, so x starts from 2. So you integrate from 2 to infinity. Okay, just be a little cautious about this. So we need to integrate the 1 over x times ln x from 2 to infinity. Again, we just do this proper integral by 2 steps. So you integrate from 2 to b, and then take the integral, take the limit with b approaching infinity. All right, so how to integrate 1 over x times ln x? So you use the substitution u equal to ln x as we did before, and it's not hard if you check it. So I recommend you, strongly suggest you to do this by yourself. What you're going to get is natural log x if you use the substitution to do the integral. Okay, and then you plug in b and 2 and subtract and then take the limit. So if you plug in b for x, you get a natural log of b minus natural log of 2. Okay, so remember, when you take the natural log of a number, you get another number. So you can take the natural log of that natural log. Okay, so now we don't have to worry about the n2, or n over n2. That's just a constant. But when b approaches infinity, then ln b approaches infinity, as we just talked about before. So then you take another natural log of that, that also approaches infinity, right? So the whole thing just approaches infinity. So the integral is divergent. That means the series also diverges. Okay, so this series 1 over n times natural log n is divergent. Okay, so this is the whole thing for this section. I don't want to do anything more than that. We just do it one by one. Okay, we're going to see a lot of these things about convergence, divergence, different techniques, and so you need a little time to digest those concepts and techniques. Usually, you have to be familiar with derivatives and the integration. Okay, all of those techniques. So this requires a little more work. when you actually work on these problems of series. So that's the whole thing about this section. I don't want to do anything more than that. And we got a couple more minutes